In July 2025, astronomers operating the ATLAS Terrestrial Impact Last Alert System (ATLAS) telescope in Chile detected a rapidly moving object that defied all expectations. Its trajectory did not match any known asteroid or comet bound to the Sun. Further analysis confirmed it was on a hyperbolic orbit, a clear sign it came from outside the solar system. Officially designated 3I Atlas, it became the third confirmed interstellar visitor in history, following 1I Oumuamua in 2017 and 2I Borisov in 2019. The I in its name marks that interstellar status. What immediately caught scientists' attention was its incredible speed, roughly 58 kilometers per second, fast enough not only to escape the Sun's gravity, but to ensure it will never return. That velocity, combined with its shallow approach relative to the ecliptic plane, indicated it had likely been wandering the Milky Way for billions of years, possibly as long as 11 billion, before a random gravitational nudge finally sent it into our neighborhood. By tracing its orbit backward, astronomers determined that 3I Atlas entered the solar system from the direction of the constellation Sculptor, inbound on a steep hyperbolic path. It will reach its closest approach to the Sun, the perihelion, around late October 2025, at about 1.4 astronomical units, roughly the distance between the Sun and Mars. Its closest distance from Earth will be around 1.8 AU, meaning there's no risk of impact. In early October, it passed near Mars, giving orbiters such as ESA's Trace Gas Orbiter and NASA's MAVEN spacecraft a unique chance to photograph it up close. To observers from Mars, it appeared as a glowing smudge surrounded by a faint coma, a visible envelope of dust and gas being released as sunlight heated its surface. From Earth's vantage point, it will fade temporarily as it passes behind the Sun, before emerging again in late December for final observations before vanishing into interstellar space forever. The early telescope images of 3I Atlas showed a compact coma and a faint, asymmetric tail. But what stunned astronomers most was its composition. It didn't behave like a typical comet at all. Spectroscopic data from ground-based observatories and space telescopes revealed that the coma was dominated by carbon dioxide rather than the water vapor that drives most comets. Measurements from the James Webb Space Telescope detected a strikingly high CO2 to H2O ratio of about 8:1, far greater than any comet previously studied. In other words, for every molecule of water it expelled, there were 8 molecules of carbon dioxide. This suggested that 3I Atlas formed in an exceptionally cold region of its parent star system, far beyond the CO2 snow line, where carbon dioxide can freeze solid, or that it had lost much of its water through cosmic ray exposure during its immense journey between stars. Supporting this, other telescopes detected little to no carbon monoxide, which is often abundant in distant comets. The data pointed to a chemically exotic body, rich in CO2 ice, poor in water, and possibly covered with a crust that suppresses normal outgassing. Adding to the mystery, several instruments detected faint Ni and Fe emission lines in its spectrum, an extraordinary finding. Normally, these heavy elements exist in solid mineral grains that don't vaporize easily at the temperatures 3I Atlas experiences. The simplest explanation is that the metals are released as volatile carbonyl compounds, such as nickel tetracarbonyl, NiCO4, and iron pentacarbonyl, FeCO5, which can evaporate at relatively low temperatures. The observed nickel-to-iron ratio was more than 10 times higher than the ratio found in the Sun, suggesting an unusual chemical environment in its origin system. Even stranger, as the comet drew closer to the Sun, the nickel-to-iron ratio began to decrease, implying that some of its metal-bearing materials break down or alter when warmed. These volatile metals hint at a formational chemistry distinct from anything seen in our solar system's comets. The coma's polarization, how sunlight is scattered by its dust, also stood out. Observations showed a deep negative polarization branch, meaning the light was polarized in a direction opposite to what is typical for comets. This could indicate unusually fine-grained dust or an exotic surface texture, perhaps altered by eons of radiation damage in interstellar space. In visible light, 3I Atlas appears greenish-white with a slightly asymmetric tail. Some images even suggested a tail pointing toward the Sun, an anti-tail, caused when large dust particles, moving more slowly than gas, create a geometric illusion from our perspective. Such backward-pointing dust features have been seen in a few solar system comets, but are rare, especially in one so distant and faint.
From a physical standpoint, the nucleus size is still uncertain. Models based on brightness and dust emission suggest it might range from a few hundred meters to several kilometers across. It is likely irregular, with patchy active areas venting gas. Hubble imaging placed an upper limit around 5 kilometers in diameter. Even at that modest size, given its density, it would carry trillions of tons of primordial interstellar material, a fragment of an alien solar system frozen since before our Sun existed. Its color, surface brightness, and gas activity suggest a relatively unprocessed object, not heavily altered by multiple stellar encounters or repeated heating cycles. If 3I-Atlas truly formed more than 10 billion years ago, that places its birth in the earliest generations of planetary systems, possibly around a long-dead star. It may have been ejected during the chaotic early stages of planet formation when giant planets scatter icy debris into interstellar space. Over billions of years, such fragments drift between stars, occasionally captured or deflected by stellar gravity. Statistical modeling implies that every star ejects billions of planetesimals over its lifetime, meaning the galaxy is filled with these cosmic wanderers. Only recently have our telescopes become sensitive enough to detect them passing through. Oumuamua and Borisov were the first clues. 3I-Atlas confirms they're not rare accidents, but part of a vast interstellar population. What makes 3I-Atlas invaluable to science is not only its rarity, but its chemical fingerprint. By studying its CO2-dominated emissions, water scarcity, and metallic traces, scientists can infer the diversity of planet-forming environments across the galaxy. Its chemistry doesn't resemble comets from our Oort cloud. implying that other stellar systems produce icy bodies with very different compositions. The presence of volatile carbonyls could even hint at prebiotic organic pathways forming under alien conditions, a tantalizing connection to the broader question of how life's chemical ingredients might spread between worlds. Some researchers have speculated that interstellar comets like this one could transport complex organics or even frozen microbes from one planetary system to another, seeding life across the galaxy. The concept of panspermia. While still speculative, each new visitor provides a test case for how matter travels and evolves in the cosmic void. Not everyone agrees on all interpretations. A few theorists, most notably Harvard astrophysicist Avi Loeb, have pointed out coincidences in 3I-Atlas's orbit, such as its near alignment with the plane of the solar system, and raised the possibility, however remote, that some interstellar objects could be artificial. He emphasizes, though, that such hypotheses require extraordinary evidence, and so far all data remain consistent with a natural origin. Still, the unusual properties of 3I-Atlas, its composition, tail geometry, and polarization ensure it will remain a scientific enigma long after it leaves our skies. As of now, 3I-Atlas continues to race sunward, gradually brightening before reaching perihelion in late October 2025. After that, it will fade rapidly as it exits the solar system, heading into the constellation Hercules at nearly 210,000 kilometers per hour. No probe or spacecraft will catch it. Humanity simply detected it too late to intercept it. But telescopes around Earth, Mars, and space will continue collecting every bit of data they can before it vanishes forever into interstellar darkness. When it's gone, only its faint dust trail and the wealth of data it left behind will remain. It is, in every sense, a cosmic messenger, a frozen relic from another star whispering secrets of worlds that perished before our sun was born. Its visit reminds us that our solar system is not isolated, but part of a vast galactic ecosystem where matter, dust, and possibly even the seeds of life drift endlessly between the stars. The interstellar comet 3ATLAS continues to defy every expectation astronomers have about cometary behavior. Unlike ordinary comets in our solar system, which always form tails pointing away from the sun due to the pressure of sunlight and the solar wind, 3ATLAS has been observed developing a tail that sometimes points toward the sun, a so-called anti-tail phenomenon that is extremely rare and typically only appears due to specific geometric alignments combined with large, slow-moving dust grains. In the case of 3ATLAS, the anti-tail appears inconsistent with standard models of dust dynamics, suggesting either a highly unusual distribution of particle sizes, unexpected electrostatic or magnetic effects in the coma, or perhaps entirely new mechanisms of dust ejection and solar interaction that have not been seen in solar system comets. Adding to the strangeness, the comet has exhibited sudden, dramatic surges in brightness, increasing up to 5 times higher than predicted by standard sublimation models, a kind of cosmic jump scare that indicates rapid releases of gas and dust or transient outbursts from localized active areas on the nucleus. These surges challenge conventional understanding of comet activity, especially for an interstellar body that may have spent billions of years in the cold, radiation-filled void between stars, which should have depleted near-surface volatiles or stabilized surface layers. Spectroscopic observations from both the Hubble Space Telescope and the James Webb Space Telescope, JWST, reveal that 3ATLAS is venting gases in a way unlike any other comet. Its coma is strongly dominated by carbon dioxide, CO2, while water vapor is comparatively weak, unusual for a comet approaching the inner solar system. Alongside CO2, traces of cyanide, CN, carbon monoxide, CO, and minor hydrocarbons have been detected. The presence of cyanide, a volatile typically associated with cometary organics, indicates that 3ATLAS may carry primordial material from its parent star system, frozen since its formation. Even more striking is that these gases are escaping the surface at distances billions of kilometers from the Sun, where the faint solar heating should be insufficient to sublimate CO2 at the observed rates. This implies that either the comet has an extraordinarily volatile-rich composition, perhaps reflecting a formation region far from its original star where CO2 ice could remain stable, or that the surface contains unique insulating or pressurized layers that allow sudden venting when sunlight penetrates cracks or weak spots. Observers also note that these outgassing events often appear irregular and asymmetric, further complicating attempts to model its behavior. Adding another layer of mystery is polarimetric data collected from ground-based telescopes, showing that 3ATLAS scatters sunlight in patterns no known comet exhibits. Polarimetry, which measures the orientation and degree of polarized light, reveals that its coma displays a deep negative polarization branch, meaning that light is being scattered in a direction opposite to what standard dust models predict. This phenomenon suggests the comet has unusual dust grain properties, possibly extremely fine or fluffy aggregates, or grains with a composition and refractive index unlike those observed in solar system comets. The combination of this unique light scattering and the anomalous anti-tail raises the possibility that 3ATLAS is not just chemically exotic, but also physically structured in a novel way, with surface and coma interactions that produce optical effects never before seen in our solar system. Scientists have described this as literally bending sunlight in a pattern we've never seen before in our solar system, a phrase that underscores how completely this object challenges traditional cometary physics.
The comet's nucleus size remains uncertain because the bright, dynamic coma obscures direct measurements, but brightness modeling suggests a diameter between 0.5 and 5 kilometers, with a likely irregular shape featuring patchy active regions. Its surface may be coated in a crust formed from refractory materials, cosmic ray processing, or previous volatile depletion, punctuated by vents that sporadically release gas and dust. The presence of rare emissions of nickel, Ni, and iron, Fe, in the coma one of the few interstellar objects for which such metals have been detected, indicates the possible sublimation of volatile metal carbonyl compounds, a process that is extremely rare and may only occur under the cold, high-vacuum conditions of interstellar space. These metals, combined with the unusual CO2-dominated chemistry, suggest a formation environment markedly different from the solar system, potentially a distant planetesimal belt around a long-dead star, preserved over billions of years in interstellar space. 3I Atlas's behavior invites natural connections to broader topics in astrophysics and planetary science. Its irregular tail and brightness surges offer an opportunity to explore dust dynamics, electrostatic forces, and magnetic effects in cometary comae. Its unusual chemical composition informs models of planet formation and volatile distribution in other stellar systems, showing that CO2-rich planetesimals can survive for billions of years and travel across galaxies. The extraordinary light scattering raises questions about particle physics and optical properties of interstellar dust grains. Furthermore, its interstellar origin touches on galactic dynamics, illustrating how objects can be ejected from one system, wander for eons, and eventually encounter another, potentially delivering organic material or even prebiotic compounds across light years. Finally, its discovery underscores the need for rapid response observational campaigns and possibly future mission concepts designed to intercept or closely study interstellar visitors, as these objects provide a rare window into the chemistry, physics, and history of planetary systems far beyond our own. In short, 3I Atlas is a cosmic enigma, a comet that defies conventional physics with its backward-pointing tail, extreme brightness surges, early and volatile-driven outgassing, and polarization patterns unlike anything seen in the solar system. It is chemically and physically alien, a fragment of a distant star system that has traveled billions of years to reach us, and it offers a once-in-a-lifetime opportunity to study the diversity of planetary bodies across the galaxy. Its anomalies are not isolated curiosities, but clues to a broader understanding of interstellar material, formation environments, and the dynamics of objects traveling between stars, connecting observational astronomy, chemical modeling, physics, and even questions of life's potential dispersal throughout the Milky Way.
While most of the world watched 3I Atlas as a rare interstellar comet, a subset of researchers began to ask a provocative question. Is this object really a comet, or could it be something far stranger? Some scientists suggested that 3I Atlas might not merely be a randomly wandering icy body, but instead a fragment of a destroyed exoplanetary system, ejected billions of years ago when massive collisions or gravitational instabilities ripped apart a planet or large asteroid belt. In this scenario, 3I Atlas would carry the chemical fingerprints of its parent star system, including volatile ices, metals, and possibly complex organics, preserved almost unchanged across the eons. Its unusual CO2-dominated coma, weak water output, and rare nickel and iron emissions lend plausibility to the idea that it formed in a chemically distinct environment, perhaps within the outer reaches of a planetary system with ice lines very different from those in our solar system. The combination of exotic chemistry and unexpected physical behaviors, like its tail sometimes pointing toward the sun and irregular brightness surges, makes it unlike any comet we have studied before, raising the question, could it be a highly processed planetary fragment rather than a typical icy nucleus? Amid these theories, Harvard astrophysicist Avi Loeb publicly asked an even more audacious question. Could 3I Atlas be artificial in origin? Could it be alien technology? He emphasized that this hypothesis is far from proven and that extraordinary claims require extraordinary evidence, but he argued that the comet's unusual composition, acceleration, tail behavior, and light scattering properties are sufficiently anomalous to warrant serious consideration of a non-natural explanation. This statement sent shockwaves through the scientific community. Most astronomers were skeptical, pointing out that hypervelocity interstellar objects are expected to display unusual behavior simply because we have almost no observational baseline for such bodies, and that known cometary physics could account for many of the anomalies. Still, the suggestion ignited a productive debate. If an interstellar object were indeed technological, how would we recognize it? And what observational criteria could distinguish a natural body from an engineered artifact? This debate naturally expands into the broader context of interstellar objects and their potential origins. Interstellar bodies like 3I Atlas are not just curiosities, they are messengers from other planetary systems, carrying clues about the conditions and chemistry of their birthplaces. If some of these objects are fragments of destroyed planets or minor bodies, their study can provide unique insight into exoplanet formation, planetary collisions, and the architecture of other solar systems. For example, a CO2-rich object with metallic outgassing might reflect formation in a system with a distant CO2 ice line and an outer volatile-rich belt, conditions very different from the solar system's Oort cloud. Detecting refractory metals like Ni and Fe in the coma also hints at processing in high-energy environments, perhaps near a star that experienced heavy radiation or supernova enrichment. Studying these compositions allows astronomers to compare planetary chemistry across the galaxy, bridging astrophysics, cosmochemistry, and planetary science in ways impossible with solar system-only samples.
The discussion also touches on how humanity could approach detecting alien technology if it ever visits the solar system. While the majority of interstellar objects are almost certainly natural, the anomalies presented by 3I/ATLS force the scientific community to consider criteria for distinguishing artificial objects. Unexpected trajectory deviations, unusual light scattering or polarization, anomalous gas emissions, or unexplainable surface or coma properties. This has inspired new theoretical frameworks and observational protocols for interstellar reconnaissance, including proposals for fast-response telescopes, targeted spectroscopy, and even hypothetical interception missions designed to study incoming interstellar objects before they exit the solar system. In essence, 3I/ATLS serves as a case study for the very question of how we'd recognize a non-natural visitor, forcing astronomers to refine both their models of natural cometary behavior and the thresholds for identifying something potentially artificial. The public and media response to the idea that an interstellar object could be alien technology has also been remarkable. Headlines ranged from cautious curiosity to sensational speculation, sparking interest not only in professional astronomy, but also in the public imagination, science fiction, and philosophical discourse.
Even though the majority consensus is that 3I/ATLS is a natural object, its unusual properties, tail orientation, extreme brightness fluctuations, CO2 dominance, refractory metal emissions, and unprecedented light polarization ensure it will remain a focal point for study and discussion for years to come. Its visit underscores the scientific value of rare interstellar travelers, which provide unmatched opportunities to test our understanding of planetary formation, interstellar chemistry, and the physical processes that govern small bodies beyond our own solar system. Finally, the case of 3I/ATLS bridges into broader questions about the nature of life and matter in the galaxy. Even if entirely natural, objects like this can serve as carriers for prebiotic molecules, offering a potential mechanism for interstellar material exchange and panspermia. By analyzing its chemical composition and physical behavior, scientists can explore how building blocks of life might survive long journeys through the cosmos. The comet's visit challenges assumptions about how rare or unusual such material is, highlighting that the Milky Way may be teeming with relics of other planetary systems, each silently wandering the stars, each capable of telling a story about worlds beyond our own. Whether 3I/ATLS is a fragment of a destroyed exoplanet, a hyper-volatile interstellar comet, or, highly speculatively, a technological artifact, it represents an unprecedented opportunity to study the galaxy up close, to rethink our understanding of small bodies, and to imagine what might lie beyond the known boundaries of natural science. Its passage is brief, but the questions it raises will resonate for decades, influencing astrophysics, planetary science, and even humanity's philosophical perspective on its place in the cosmos.
Observing 3I Atlas has required the combined power of the world's most advanced telescopes, both in space and on the ground, each contributing unique insights into this interstellar visitor's physical and chemical properties. The Hubble Space Telescope provided the first high-resolution images of its nucleus and surrounding coma, revealing a compact, icy core partially shrouded in a halo of dust. Hubble's imaging allowed astronomers to measure the comet's approximate size, estimate its dust production rate, and track the evolving shape of its tail. These observations were critical for understanding the spatial distribution of material being ejected and provided a baseline for monitoring its activity over time. Meanwhile, the James Webb Space Telescope, JWST, took the study of 3I Atlas to a new level by analyzing its infrared spectrum, identifying the chemical fingerprint of gases such as carbon dioxide, CO2, carbon monoxide, CO, cyanide, CN, and minor hydrocarbons. JWST's observations confirmed that the comet's outgassing was strongly CO2-dominated, with relatively weak water emissions, and that the ratios of these volatiles were unlike those seen in typical solar system comets. This chemical information allowed researchers to infer formation conditions in its parent star system, suggesting that 3I Atlas formed far from its star, in a cold, volatile-rich environment, and had remained largely unaltered during its billion-year journey through interstellar space. Interestingly, 3I Atlas was first glimpsed even earlier, in May 2025, before its formal discovery, by the Transiting Exoplanet Survey Satellite, TESS, whose primary mission is to hunt for exoplanets. Although TESS was not designed for comet observation, its sensitive wide-field imaging captured the object serendipitously, enabling astronomers to trace its initial approach trajectory, early outgassing activity, and gradual brightening. These pre-discovery observations provided an invaluable temporal baseline, showing that the comet had been active far from the Sun, and that its volatile release began earlier than expected, consistent with CO2 sublimation rather than water-driven activity. On the ground, large telescopes such as Gemini South in Chile and the TRAPPIST South Telescope Array independently confirmed 3I Atlas's rapid evolution, including sudden increases in brightness, tail development, and asymmetrical dust patterns. Spectroscopic measurements from these observatories allowed real-time monitoring of gas emissions and dust composition, complementing space-based data and providing the ability to track temporal variations with high cadence. These combined efforts showed that the comet's coma and tail morphology were highly dynamic, changing noticeably even over the course of a single night, indicating localized sporadic jets of gas and dust from the nucleus. Polarimetric observations, made possible by some of the largest ground-based telescopes, revealed that 3I Atlas scatters sunlight in unprecedented ways, exhibiting a deep negative polarization branch and unusual angular dependence, suggesting a dust population composed of extremely fine or fluffy particles with unique refractive properties. Observatories with adaptive optics further captured high-resolution imagery of the tail, confirming the existence of anti-tail features where dust appeared to stream toward the Sun under certain viewing geometries. Multi-wavelength campaigns spanning ultraviolet, visible, and infrared bands allowed scientists to separate gas and dust contributions to the coma and measure outflow velocities. These studies confirmed that the comet's brightness surges, sometimes 5 times higher than predictions, were tied to episodic releases of CO2-rich gas carrying entrained dust, rather than being caused solely by changes in viewing angle or distance. In addition, the coordinated effort between space-based and ground-based instruments allowed continuous tracking of the comet as it moved behind the Sun from Earth's perspective, ensuring that no major events were missed despite observational gaps.
The Global Observing Network has also enabled the identification of rare metallic emissions, including nickel and iron, suggesting the sublimation of metal carbonyl compounds. These detections were made possible by high-dispersion spectrographs on telescopes such as the Very Large Telescope, VLT, and Keck Observatory. The simultaneous multi-instrument approach allowed astronomers to correlate changes in metallic emissions with variations in CO2 outgassing, providing clues about the internal composition and structure of the nucleus. The coordinated observations also help contextualize 3I RATLS within the broader population of interstellar objects. By comparing its activity, composition, and morphology to those of Oumuamua and 2I Borisov, scientists can begin to understand what traits are typical of interstellar visitors versus those that are unique to 3I RATLS. For example, while 2I Borisov was water-rich and chemically similar to solar system comets, 3I RATLS exhibits an unusual CO2-dominated composition and rare metallic emissions, highlighting the chemical diversity of planetesimals formed around other stars.
These extensive observations also facilitate speculation and hypothesis testing about its origin and potential implications. If 3IRATLS is a fragment of a disrupted exoplanetary system, the combination of CO2 dominance, metal content, and dust morphology provides direct evidence of planetary processing in another star system. Furthermore, its unexpected behavior, anti-tail formation, polarization anomalies, and episodic brightness surges challenges conventional models of cometary physics and encourages development of new theoretical frameworks for interstellar comet activity, dust-gas interactions, and sublimation physics. From a practical perspective, this observational campaign demonstrates the necessity of rapid response, multi-platform coordination for studying transient interstellar phenomena. Instruments optimized for other purposes, such as TESS for exoplanet hunting or JWST for infrared spectroscopy, proved invaluable in supplementing dedicated cometary observations, illustrating the versatility and global collaboration required to fully characterize an object traveling at tens of kilometers per second across interstellar space. Finally, the extensive data set collected from Hubble, JWST, TESS, and ground-based telescopes lays the foundation for long-term analysis of 3IRATLS and similar objects. Its passage provides a unique laboratory to study interstellar chemistry, planetesimal evolution, and the potential delivery of organic compounds between stellar systems, connecting physical observations with broader questions about the composition, formation, and migration of matter across the galaxy. In short, the world's eyes on the sky, from orbiting space observatories to the largest ground-based telescopes, have allowed astronomers to watch 3IRATLS in unprecedented detail, capturing its icy heart, dynamic tail, and chemical secrets, offering insights that will influence astrophysics, planetary science, and even the search for life beyond our solar system for decades to come.
The chemical makeup of 3I Atlas reveals a composition unlike any comet studied in our solar system, offering an unprecedented glimpse into the conditions of distant star systems. Observations indicate that it releases roughly 8 × 10⁻³ cyanide, or CN, molecules per second, a staggering quantity that emphasizes the comet's highly active nature despite its interstellar journey. Spectroscopic analysis shows that the object is carbon chain depleted, lacking the longer hydrocarbons commonly found in solar system comets, such as complex polyions and nitriles, which are typically products of chemical evolution within the protoplanetary disk. This depletion suggests that 3I Atlas formed in a stellar nursery with a fundamentally different chemical environment, one either colder, more irradiated, or less rich in carbon-rich dust, indicating that planetesimals formed around other stars can exhibit chemical fingerprints dramatically distinct from those we are familiar with. This is consistent with its CO2-dominated outgassing and comparatively weak water emission, pointing to a volatile inventory shaped by both primordial conditions and billions of years of interstellar radiation processing. In addition to CO2 and CN, 3I Atlas is likely enriched in hypervolatiles, such as molecular nitrogen, N2, and hydrogen, H2, which sublimates at extremely low temperatures. These volatiles enable the comet to become active at distances far beyond the orbit of Jupiter, much earlier than typical solar system comets, which primarily rely on water sublimation closer to the Sun. Infrared spectroscopy from JWST, combined with ground-based observations,
confirms the presence of these hypervolatiles, explaining the comet's early onset of activity observed even in May 2025 by TESS. The release of these gases is not uniform, occurring in intermittent jets that produce the asymmetric coma and sudden brightness surges, sometimes multiplying the comet's luminosity by several times over short periods. This behavior underscores the fact that 3I Atlas is chemically and physically primed for high activity, despite the extreme cold of interstellar space during its multi-billion-year voyage. One of the most visually striking aspects of 3I Atlas is its emerald green glow, first noted in high-resolution imaging by Hubble and confirmed with spectroscopic filtering in ground-based observations. This green coloration is likely caused by excited diatomic carbon, C2, in the coma, which fluoresces under sunlight, producing the eerie green light historically described in observations of comets across human history. The intensity of this glow is amplified by the comet's high carbon-to-hydrogen ratio and the lack of long-chain hydrocarbons, which would otherwise absorb or re-emit light differently. The green coma, in combination with rare metallic emissions like nickel and iron carbonyls detected in the gas, paints a picture of a chemically exotic body whose surface and near-surface layers are rich in reactive, volatile compounds that respond dynamically.
The elemental and molecular inventory of 3I Borisov Atlas offers clues to its formation environment and evolution. Its carbon chain depletion and CO2 dominance suggest formation in the outer reaches of a protoplanetary disk, likely beyond the CO2 and N2 snowlines, where temperatures were low enough to allow these ices to condense, but insufficient for longer carbon chain molecules to form efficiently. Over billions of years drifting through interstellar space, exposure to cosmic rays, ultraviolet radiation, and occasional stellar encounters may have further processed its surface, depleting weaker molecules, creating refractory crusts, and concentrating the remaining hypervolatiles. This long-term irradiation may also explain the comet's unusual polarization of scattered light, its antitail phenomena, and sporadic brightness surges, linking its chemical composition directly to its observed anomalous behaviors. The presence of cyanide and other simple organic molecules also raises questions about the potential for prebiotic chemistry in interstellar objects. While highly speculative, the fact that 3I Borisov Atlas carries chemically reactive compounds preserved across billions of years suggests that interstellar comets could transport building blocks for life across stellar systems. The combination of CO2, CN, hypervolatiles, and excited C2 provides a unique laboratory for understanding how planetary systems distribute and preserve organic and volatile material, revealing the chemical diversity of extrasolar planetesimals. By studying these molecules, astronomers can infer not only the temperature, pressure, and radiation conditions of its parent system, but also the likelihood that similar interstellar objects might seed young planets with volatile compounds and simple organics. Finally, 3I Borisov Atlas's chemical signature complements the global observational effort. Hubble's imaging, JWST spectroscopy, TESS's early detection, and ground-based telescope data together create a holistic picture of its chemistry in action, from outgassing rates and volatile composition to dust and metallic content. This synergy enables a rare, real-time chemical analysis of a body traveling at 58 kilometers per second through interstellar space,
providing unprecedented insight into the physics and chemistry of extrasolar planetesimals. In essence, 3I Berisov Atlas is more than a comet. It is a time capsule of cosmic chemistry, a messenger carrying molecular secrets from another star system, challenging our understanding of cometary diversity and offering a window into the fundamental processes that shaped the galaxy's planetary building blocks.
3I Atlas is not just unusual in its chemistry and behavior. Its trajectory tells a story that stretches across the galaxy. Unlike comets from the solar system's Oort cloud, which are gravitationally bound to the Sun and follow elliptical orbits, 3I Atlas travels along a hyperbolic path, meaning it is unbound and arrived from another star system. Its incoming velocity of roughly 58 kilometers per second, combined with its steeply inclined orbit relative to the ecliptic plane, makes it almost impossible to have originated within the solar system. Dynamical modeling indicates that this interstellar traveler may have been wandering the Milky Way for up to 11 billion years, its path shaped by gravitational nudges from passing stars, galactic tides, and interactions with interstellar clouds. In essence, it is a fragment of cosmic history, a relic from another system that survived ejection into the cold, radiation-filled void between stars. The physical and chemical properties of 3I Atlas provide further clues to its formation environment. Its CO2-dominated composition, carbon chain depletion, and traces of hypervolatiles like nitrogen and hydrogen suggest it formed in the outer regions of a protoplanetary disk beyond the CO2 and N2 snowlines, where temperatures were low enough for these ices to condense, but high-mass carbon chains could not easily form. One scenario is that it originated in a planet-forming disk around a star that has long since died, possibly scattered into interstellar space by gravitational interactions with giant planets or by a supernova explosion. Its unique chemical signature acts like a cosmic fingerprint, offering direct insight into the diversity of planetesimal formation in extrasolar systems. Every atom, from volatile gases to refractory metals, carries information about temperature, pressure, and radiation conditions in its home system, effectively turning 3I Atlas into a natural sample return mission from interstellar space, a treasure trove of material that would otherwise be inaccessible without decades of interstellar travel. Astrophysical simulations suggest that objects like 3I Atlas are relatively common in the galaxy, even if rarely observed, with billions of icy planetesimals ejected from planetary systems over their lifetimes. Its journey likely spanned hundreds of light years, crossing interstellar space, largely unaltered, though exposed to cosmic rays and ultraviolet radiation that could modify surface chemistry, deplete fragile molecules, and generate crusts of refractory material. These processes may explain some of the comet's observed anomalies, including its unusual anti-tail, sporadic brightness surges, and polarization patterns. Unlike solar system comets that have experienced repeated perihelion passages, 3I Atlas is a primordial relic, essentially untouched by repeated solar heating, preserving chemical and isotopic information from its parent system in near original form.
The study of its origins also links directly to broader galactic dynamics and planetary science. By modeling its inbound trajectory and possible past stellar encounters, astronomers can estimate the type of star system it came from, the likely architecture of its original planetary system, and the mechanisms that could have ejected it into interstellar space. For example, ejection could occur during early planetary migration phases when forming giant planets scatter icy debris, or through catastrophic events such as stellar death or close encounters with other stars. Such insights allow scientists to compare planetary formation and evolutionary processes across the Milky Way, expanding understanding beyond the biases of our own solar system. Additionally, 3I ATLS has implications for panspermia and interstellar material exchange. Its content of cyanide, CO2, nitrogen, hydrogen, and simple organics suggests that interstellar objects can transport volatile and potentially prebiotic compounds across vast distances, seeding other star systems with the raw ingredients for life. While speculative, this makes 3I ATLS more than a curiosity. It is a messenger carrying material that could inform the chemical evolution of other planetary systems, providing rare empirical data to validate models of how matter migrates through the galaxy. Observationally, its interstellar origin underscores the importance of global telescope coordination. Space-based instruments like Hubble and JWST, ground-based giants like Gemini South, TRAPPIST-South, VLT, and Keck, and even serendipitous detections from TESS have together captured its trajectory, chemical fingerprint, and activity in real time. By combining orbital modeling with spectroscopic, photometric, and polarimetric data, astronomers can trace both its path and its evolutionary history, building a multi-dimensional picture of an object formed around a distant star billions of years ago. In essence, every photon collected from 3I ATLS tells part of the story of its origin, journey, and the processes that shaped it long before it entered our solar system. The Stranger story is thus not just about a comet passing by. It is a window into the broader processes that govern the Milky Way, revealing how planetary systems form, evolve, and exchange material across cosmic distances. By following 3I ATLS, astronomers are learning not only about a single alien world, but also about the interconnected chemistry and dynamics that shape our galaxy, bridging observational astronomy, planetary science, and
The discovery of 3I Atlas in July 2025 set off an unprecedented frenzy in the astronomical community, demonstrating how modern science responds in real time to a rare cosmic visitor. At first, only 4 scientific papers referenced the object, as astronomers scrambled to confirm its unusual hyperbolic trajectory and collect preliminary data on its brightness, orbit, and composition. Within just 2 months, that number skyrocketed to more than 70 peer-reviewed publications, reflecting the global effort to characterize every aspect of this interstellar comet before it reached perihelion on October 30, 2025, its closest approach to the Sun. This rapid response highlights the collaborative nature of contemporary astronomy, where space-based observatories, ground-based telescopes, and even amateur astronomers worldwide can contribute critical observations, and discoveries are shared almost instantly across the scientific community. The sheer pace of research illustrates how humanity has entered an era in which cosmic phenomena can be studied almost as they unfold rather than months or years after the fact.
The observational campaign for 3I Atlas is both wide-ranging and multidisciplinary. Spacecraft like SOHO, Solar and Heliospheric Observatory, and SPHERIX, while designed for solar monitoring and cosmic infrared surveys respectively, have contributed valuable data on dust and gas emissions, revealing details about the comet's activity near the Sun and helping track its evolution. Mars orbiters, particularly MAVEN, provided an alternative vantage point, imaging the comet as it passed near Mars and offering high-resolution measurements of the coma and tail from a different perspective. Ground-based telescopes, ranging from professional giants like Gemini South, VLT, and Keck, to smaller automated arrays such as TRAPPIST South, have delivered high-cadence photometric, spectroscopic, and polarimetric data. Even amateur astronomers worldwide have contributed time series imaging, helping to monitor rapid changes in brightness, tail formation, and dust outbursts. This integration of professional and citizen science demonstrates the power of coordinated observations, especially for transient, fast-moving interstellar visitors whose behavior changes on timescales of hours or days. Real-time discovery and monitoring have been essential because 3I Atlas is not a typical comet. It exhibits unpredictable and dynamic behavior. Its brightness has surged sporadically, sometimes 5 times higher than predictions, due to episodic jets of CO2-rich gas and dust. The tail occasionally points toward the Sun, forming anti-tail structures, and polarimetric measurements reveal unprecedented scattering patterns of sunlight. Capturing these phenomena as they occur allows scientists to correlate them with chemical composition, outgassing rates, and nucleus properties, linking observations directly to physical models. Spectroscopy from JWST and Hubble, along with ground-based high-dispersion instruments, have quantified emissions of CO2, carbon monoxide, cyanide, and rare metals like nickel and iron, providing insights into how the comet's interior composition drives surface activity. Real-time monitoring also enables tracking the onset of hypervolatile activity at extreme distances from the Sun, which would be missed if observations were delayed until the comet neared perihelion. The rapid influx of data has triggered cross-disciplinary collaboration. Astrophysicists, planetary scientists, chemists, and dynamicists are jointly modeling the comet's trajectory, chemistry, dust physics, and potential origin scenarios. Computational simulations now explore its likely birth in a distant protoplanetary disk, ejection mechanisms, and billions of years-long interstellar journey. Researchers are also evaluating hypotheses about its anomalies, including the possibility of being a fragment from a destroyed exoplanetary system, or, in the most speculative discussions, whether some of its unusual features could hint at non-natural origins, a topic that, while controversial, has spurred new thinking about how to identify artificial interstellar objects. This collaborative approach ensures that the science of 3I Atlas is not siloed, but examined from multiple perspectives, combining observational data with theoretical modeling in near real time.
The timing of the perihelion pass amplifies the urgency. On October 30th, 2025, 3I Atlas will reach its closest distance to the Sun, approximately 1.4 astronomical units, where solar heating will maximize its activity. Every observation prior to this point is critical for establishing baseline data and understanding its behavior under minimal solar influence. After perihelion, The comet will recede and rapidly fade as it exits the solar system forever, limiting opportunities for follow-up. This narrow observational window has led to unprecedented international coordination, with telescopes scheduled to cover every possible spectral band, from ultraviolet to far infrared, and from multiple angles. Real-time analysis pipelines allow teams to respond instantly to changes in brightness, outbursts, or tail dynamics, capturing events that might otherwise be missed in retrospective surveys. The scientific impact of this campaign extends beyond 3I/Atlas itself. By coordinating observations of an interstellar object moving at tens of kilometers per second, scientists are testing the limits of telescopic instrumentation, data sharing, and modeling techniques. The discoveries inform not only cometary physics, but also exoplanetary system formation, galactic dynamics, and interstellar chemistry, offering a rare glimpse into the building blocks of planets from other stars. Every photon collected contributes to understanding how hypervolatiles, CO2-rich ices, metals, and organic molecules behave under interstellar and near-solar conditions, effectively making 3I/Atlas a moving laboratory for planetary science and astrochemistry. The unprecedented pace of research demonstrates that humanity can now study interstellar objects in real time, transforming a brief cosmic encounter into a definitive window onto the galaxy's hidden diversity. In short, the scientific response to 3I/Atlas exemplifies modern observational astronomy at its most agile and collaborative, blending space-based and ground-based instruments, professional and citizen science, and theoretical modeling. From the initial detection to the flurry of publications and coordinated observations, this object has catalyzed a research effort that is both rapid and comprehensive. As it races toward perihelion and prepares to exit our solar system forever, 3I/Atlas reminds us that the galaxy is full of transient messengers, and with the right technology, collaboration, and analytical frameworks, humanity can observe, understand, and learn from these visitors in real time, capturing secrets of other star systems that would otherwise remain forever beyond our reach.
As 3I/Atlas speeds through the inner solar system, astronomers are facing a cosmic cliffhanger. What will happen to this mysterious interstellar visitor as it encounters the Sun? Its perihelion on October 30, 2025 marks the closest approach, where solar heating will reach its peak, testing the comet's structural integrity and volatile inventory. Many comets fragment or disintegrate under similar conditions, especially those composed of loosely bound ices and dust, and 3I/Atlas's unusual chemical composition raises unique questions. Its surface appears to contain highly volatile CO2, CO, cyanide, nitrogen, and hydrogen, along with traces of metals like nickel and iron. Unlike typical solar system comets, which have been thermally processed over multiple orbits, 3I/Atlas is largely pristine, having traveled billions of years through interstellar space, meaning its nucleus may be more fragile than it appears. The possibility of catastrophic breakup looms, but equally plausible is that it will survive largely intact, continuing its journey out of the solar system, carrying invaluable information about another planetary system across the galaxy.
The stakes of this encounter extend beyond structural survival. 3I Atlas presents an unparalleled opportunity to test and refine models of cometary physics under extreme conditions, particularly for interstellar bodies. Its episodic brightness surges, anti-tail formation, unusual polarization patterns, and hypervolatile outgassing all challenge current understanding of sublimation, dust-gas interactions, and nucleus mechanics. Observing how these phenomena evolve under intense solar irradiation will allow scientists to validate theoretical models of interstellar comet activity and possibly discover new physical processes that do not occur in native solar system comets. Any fragmentation or sudden increase in outgassing could provide rare direct evidence of internal layering, pressure dynamics, or crystallization fronts, effectively turning 3I Atlas into a real-time laboratory for high-energy cometary physics. Its chemical profile also promises continued surprises. The comet's carbon chain depletion, CO2 dominance, and rare hypervolatiles offer insight into planetesimal formation in other stellar systems, and perihelion may expose previously hidden layers. Sublimation of deeply buried volatiles could reveal unknown molecular species, some of which may survive only under the extreme cold of interstellar space and have never been observed in solar system comets. The potential discovery of such compounds could reshape our understanding of interstellar chemistry, showing how star-forming regions produce materials that are then transported across the galaxy. In particular, the observed emerald green glow from diatomic carbon, C2, may intensify or fluctuate, providing clues to photochemical reactions and energy transfer within the coma, while metallic emissions could reveal refractory processing under intense solar irradiation.
The encounter also carries profound implications for planetary science and galactic dynamics. If 3IA Atlas survives perihelion, astronomers will have the first opportunity to track an interstellar object's post-solar system trajectory with precision, constraining its original ejection point, past stellar encounters, and travel path across the Milky Way. Combined with chemical and physical data, this allows scientists to reconstruct the history of a single object from another star system, providing a unique window into the formation and evolution of extrasolar planetesimals. Conversely, if the comet fragments, the resulting debris trail may create a mini-laboratory in the inner solar system, allowing measurement of particle size distribution, volatile fractionation, and dust-gas interactions in unprecedented detail. Either outcome enriches our understanding of the lifespan, resilience, and chemical diversity of interstellar objects. Beyond the strictly scientific, 3IA Atlas sparks imagination and broader contemplation. Its anomalies, from tail orientation and brightness surges to unusual light scattering and rare metallic emissions, push scientists to question assumptions about natural processes and consider extraordinary possibilities, including fragments of other planetary systems, or even, speculatively, the limits of engineered interstellar material. Even without invoking artificiality, every observation challenges researchers to expand their conceptual framework. How are planetary systems distributed? What processes dominate in different stellar nurseries? And how common are volatile-rich, chemically unique bodies wandering between stars? Each new dataset from Hubble, JWST, SOHO, TESS, Sphere X, MAVEN and countless ground-based observatories contributes to a story that blends astrophysics, chemistry, planetary science, and galactic evolution. In the end, 3IA Atlas embodies the essence of discovery: unpredictable, fleeting, and profoundly enlightening. A cosmic cliffhanger that will influence astronomy, planetary science, and our understanding of the Milky Way for decades to come.
3I Atlas is not just another comet. It is a real interstellar visitor that provides students and scientists alike with a tangible example of the dynamic, interconnected cosmos. Unlike fictional portrayals of alien comets, this object has been directly observed and measured, traveling at 58 kilometers per second on a hyperbolic trajectory that proves it originates from another star system. Its discovery in July 2025 marked only the third confirmed interstellar object detected in the Milky Way, following Oumuamua in 2017 and 2I Borisov in 2019. However, 3I Atlas is remarkable even among these rare visitors. It exhibits extreme brightness surges, unusual tail behavior, anti-tail features, and unprecedented polarimetric properties, making it potentially the most active and chemically diverse interstellar object discovered to date. Students learning about this comet are witnessing science in real time, seeing how astronomers respond to new discoveries, rapidly publish data, and coordinate global observational campaigns to extract as much knowledge as possible before the object exits the solar system. One of the most compelling lessons 3I Atlas offers is how it reveals the diversity of planetary systems across the galaxy. Its unusual chemical composition, dominated by CO2, hypervolatiles like nitrogen and hydrogen, and significant cyanide release, combined with a carbon chain depletion unlike typical solar system comets, points to formation in a stellar nursery very different from our own. Observing these characteristics allows students to understand that planets and minor bodies are not uniform across the cosmos. Rather, each planetary system produces planetesimals with unique chemical fingerprints and histories, influenced by the temperature, radiation, and composition of their birth environment. Even the emerald green glow caused by excited diatomic carbon, C2, illustrates how chemical properties translate into observable phenomena, connecting molecular physics with celestial mechanics in ways that make astronomy both tangible and intellectually stimulating. The comet also provides a hands-on lesson in real-time science, demonstrating how discoveries are studied collaboratively across multiple platforms. From space-based instruments like Hubble, JWS